Hi, I'm Abby Frank, and I'm the project manager of Purdue Space Program High Altitude. This is our first year competing in the Argonia Cup and our first year building a two-stage rocket. We have 7 subteams that have all contributed to this rocket in many different ways: avionics, simulations, manufacturing, structures, mechanisms, business, and propulsion. You'll hear from them in this video today. We're so excited to be learning so much throughout this process, and we're excited to tell you about our design.
Hi, I'm Christina, and I'm a project engineer. From composites manufacturing to electronics design to mixing and casting custom motors, each new project is a wonderful opportunity for students to get hands-on experience building, testing, and launching rockets. High Altitude hopes to continue pushing Purdue's altitude record for student rocketry.
Hi, I'm Michaela. I'm the structures lead. Our rocket is Event Horizon. It was designed for this Argonia competition. It's about 117 inches tall and weighs about 14 pounds. It's made entirely out of G10 fiberglass, except for a carbon fiber lamp over the fins for stability. For motor retention, we have forward motor retention on the sustainer with an Aeropack motor retainer, and the booster has friction fit motor retention. Our interstage design is a motor coupler design. So the motor from the sustainer fits into the booster airframe. And then underneath that, we have what we're calling an interstage cup that's been manufactured to seal the pressures from the motor ignition, as well as have a hard point for the chutes to connect to and kind of act as a nose cone for the booster once it's separated. As part of the competition, our payload is going to be golf balls. We're fitting them in the airframe with a compression fit between pieces of foam to prevent extra vibrations that may affect the integrity of the rocket.
Hi, I'm Carrie. I'm the manufacturing lead. So I'm responsible for the manufacturing of the interstage coupler and the bulk plates on Event Horizon. The bulk plates are an attachment point for the avionics bay and also a hard point for the recovery system. And along with that, the interstage coupler is a mission critical piece that was manufactured on the machines here at Bechtel.
I'm Owen. I'm a project engineer. This past weekend, we completed the first 2 launches of our 5 test launch campaign. The first launch successfully demonstrated that we were able to recover both stages even without a sustainer motor light. In the second test launch, we were able to successfully demonstrate that we were able to fly a 2-stage rocket, lighting both motors and successfully recovering both stages. Following this, we'll complete the final 3 test launches of our 5 test campaign. The third launch will be similar to the first 2, with subscale motors, just slightly more powerful. The 4th and 5th flights will be with a competition booster and then a competition sustainer motor to demonstrate that the rocket stages can handle the competition motors.
Hi, I'm Travis. I'm the Sims lead. The major role for the simulations team for Argonia was to balance having a rocket which performed well with having a rocket that we could feasibly build and that all the sub-teams felt comfortable with. A major contributing factor was the diameter of the rocket. Usually our rockets are about 4 inches in diameter. This time, because of drag reasons and performance reasons, we chose to have a 2.242 inch outer diameter rocket, which corresponds to 54 millimeter motors. This is obviously much smaller than what we usually do, and there's a lot of back and forth between the avionics and the other teams talking about how we can actually fit all of the components we usually have into this smaller space.
Hi, I'm John. I'm the propulsion lead. We're using an Aerotech DMS system L1000 for our booster motor. We'll be lighting that with the standard igniter. And for a sustainer, we'll be using a Loki K250, lighting with a combination of an E-match and a Pyrodex pellet.
Hello, my name is Brett. I'm the mechanisms lead. Yeah, of course. So both stages is going to have just one parachute. The first stage, the booster stage, will have a parachute that comes out immediately at apogee. Each parachute will be wrapped in a Nomex blanket and have 2 charges, one primary charge and one backup charge. The booster parachute will come out at apogee and immediately unfold to slow the descent to a safe speed. And for the sustainer, it'll have the same process, except the parachute will remain folded in that Nomex blanket due to cable cutters. So it'll act as a streamer as it comes down to a safer height to reduce drifting. And then that cable cutter will activate at about 1,000 feet and let the parachute unfold to allow a more safe descent rate. So the black powder charges we make are self-made. We use a process called glove tip charges, which is using the tip or fingertip of a nitrile glove. We initially do a base calculation to calculate how much force is needed to separate the rocket and use a general amount of black powder we think will do that calculation. And then we do a separation test inside the rocket to make sure that the black powder does separate the rocket safely without burning parachutes or Nomex blankets in the process.
Hi, I'm Griffin. I'm one of the avionics leads. So PAL 9000 is our custom SRAD flight computer. SRAD means Student Research and Develop, which means that our entire team has been working to develop this completely on their own. And what's amazing about that is it allows us to really learn everything about the electronic design process and get experience that we don't normally get in our classes. So the elements that go into PAL are fully working GPS, a whole suite of sensors, a large storage, and some of these actually beat off-the-shelf solutions. And what that allows us to do is kind of test the limits of what might be needed for a flight computer and experiment with new things. PAL on Event Horizon is primarily a backup flight computer. And it does actually handle backup staging operations. And that happens through a state estimation algorithm that we've developed over time and tested on numerous flights. And that really allows us to get a whole lot of experience in data processing and then try to put that into practice in the way that commercial flight computers would. And we found really good success in that. And it's been very reliable. So we're excited to have it on Event Horizon doing the same thing again and hopefully working very reliably.
Hi, I'm Adam. I'm one of the avionics leads. Our main priority for avionics is the safety of our team and the people around the launch. This includes a lot of things, including angle lockouts for staging, as well as ensuring that no charges have any potential of going off until everybody is clear of the rocket, as well as design choices, including like redundancy, transmissions are able to see the location of the rocket, and other things like that. The second stage will be using several lockouts to ensure that ignition happens only when it's safe, including tilt lockouts, tilt rate lockouts, so predicted tilt in the future, and velocity lockouts to ensure that the rocket only ignites when pointed upward at a safe speed at a safe altitude. We also have a time-based lockout to ensure that the upper stage ignites after the lower stage is finished igniting and ignites before separation charges go off, which could throw it askew. If a flight computer fails, our flight is still able to continue safely, if not maybe successfully. If our COTS flight computer fails, for example, we aren't able to ignite the upper stage, but we are able to safely recover the rocket. If our SRAD computer fails, we are able to stage. However, we have to use our backup tracking method for relocating the rocket after landing.
Thank you for learning more about Event Horizon. The challenge presented by the Argonia Cup has given us the opportunity to design and test rockets in exciting new ways. We're really looking forward to seeing everyone in Kansas in a few weeks. Boiler up.